Hi, this is the fifth video in the probability section, and this one is, well, I've just called it other methods because we've looked at probability trees, we've looked at Venn diagrams, we've looked at Bayes rule as well, and kind of linked that in with probability trees. But there are a couple of other things that are kind of worth knowing about, which, for the sake of anything else, we just called it other methods. Okay, so now this first one really is, I think, we're getting at here is that we use probability trees are very useful, but sometimes probability trees can be very cumbersome to draw. I mean, if we've got three levels of branches and, each of the outcomes has got, or each node gives rise to maybe three, possibly four different events, then you can see that the probability tree can get quite complicated quite quickly. Also, we don't always need all the nodes. We don't all the leaves. If they don't actually help us answer any of the questions, we might not really need to do it. So in general, if we can adopt the thinking of a probability tree, but maybe use a little bit of notation and make it more concise and save a lot of time, basically. So this question helps to illustrate that. It's a slightly complicated question, but it does kind of bring out the gist of it, really. So let's have a look at it. A bag contains tokens that each have a single number written on them. The integers between 1 and 15 are all represented on the tokens. Yeah. There is one token with a 1 on it, two tokens with a 2, and or so on until 15 tokens with 15. So there's a 1 plus 2 plus 3 plus 4. So there are, well, this is the 15th triangle number. So the total number of tokens is 120. So that's 120 tokens, discs or whatever they are, in a bag. Okay, and a token is taken from the bag and the number on it is recorded but not replaced in the bag. Okay, so this is a probability tree without replacement. A second token is then taken from the bag and the number on it is recorded. Using a tree diagram or otherwise, work out the probabilities of the following events. The numbers on the two tokens are neither both prime nor both square numbers. Now, this gives us a hint, really, as to the notation that we're looking at, because we've got primes, we've got squares, and then we've got not prime or square, so P, S, or N. So we've kind of got, can imagine nodes with three branches coming away from them, a P, an S, and an N. So let's have a look. We've got primes 2, 3, 5, 7, 11, 13. Now, I've got all those up because there are 2 with 2 on, 3 with 3 on, and so on. So all that adds up to 41. So there are 41 out of the 120 tokens that have prime numbers on them. And the squares are 1, 4, and 9. So there are 14 that have squares on them, and then the rest that have neither a prime nor a square, it comes to 65. That's what's left out of the 120. Okay, so now what I've done here is I've just gone down and actually produced what is essentially the leaves of the probability tree. We might not even need to do this, actually. You'd have to look at the question. I mean, you know, very often you can just calculate the leaves for the things that you're particularly interested in. So if you have a look at the question, you will see. But here anyway, I've done all the leaves, and let's just have a look. So this is the intersection of P and P. So this would be where you draw a prime number token out. as your first one. You keep it, and then you draw another one out, and that's a prime as well. So that's 2 primes. Now, what we're actually saying is, on the first pick, the chance of getting a prime is 41/120ths. Okay. Then on the second pick, because you've got one fewer prime left in the bag, so there's only 40 left, and there's only 119 tokens in the bag in total now. So the probability on the second draw of getting another prime would be 40 divided by 119. Okay, so we could write that out as, you know, this product divided by this product. But we're just going to keep it like this for the moment, and I think that will become clear. Okay. All right, so this is thinking that we've applied on probability trees before. Probability of a prime and then a square would be 41. And then on the second pick, when there's only 119 left in the bag, we've still got 14 squares, and so on. So we can just work our way through there. A product, possibility of a knot and a prime would be 65 on the first draw, and then we've still got our 41 primes left in the bag of 119 there, so that'll be 41/119ths. So that's what that would be. That's how we work out all those out. So this is the probability of P intersection P, and so on. Okay. Now, if we actually multiply those two together, we get these numbers in the right-hand column. This product here, it comes to this 14,280. Bit of a big number, but so if we add all these up, we get 14,280. And as probabilities, of course, they're all divided by 14,280. So this probability is actually 1640 divided by 14,280, and so on. But we're quite happy to keep these just as numbers, and I'll show you why in a moment. Okay, so this is our leaf table. We filled in all the leaves, and just to re-emphasize, we may wish in similar problems just to actually do the leaves that we're interested in, and not all of them. Okay, so part 1 of the question, the numbers on the 2 tokens are neither both primes nor squares. Okay, so the numbers on the 2 tokens are neither both primes nor both squares. Okay, right, I've answered a different question here, but well, let's just run with it. So the thing that I've calculated here is the probability that they're neither of them are primes or squares. So my slip up there, but let's pretend the question was different. So that would be given by n, and that's just simply this here, 4160 divided by 14,280, which is this fraction, which works out as 0.291 to 3 decimal places. Okay, so that's a fairly straightforward one. Well, I made it even more straightforward than it should have been, but second one, the number on one of the tokens is a prime number. Given given this is a conditionality, of course, given that the numbers on the 2 tokens are neither both prime numbers nor square numbers. Right, okay, so number 2 is given by 1 is P, given that they're not, that the pair of them together are not PP and not SS. Okay, so that would mean that we could have PS, SP, SN, NS, and obviously given that they're not PP or SS. Now, what we're actually doing by this conditionality, it's a slightly different treatment to what we've done in the previous video, but we're essentially, our total probability space of 1 we've kind of reduced it. We've taken these two rows out, if you like. And as a result, we would, if we wanted to then sort of say, well, these are all the things that can happen, therefore they must add up to 1. We would have to scale all these things accordingly. So what we are in effect doing is dividing these probabilities by 1 minus that. This is the total probability of everything that's left. Okay, so it's the probabilities of the things which pass our test in the question, divided by the total probability space, excluding the ones that we're told it's not, as in the question. Okay, so that's what we're doing, excluding those. So yeah, so we've got the probability of PS plus the probability of SP plus probability of SN plus probability of NS. Okay, these are all mutually exclusive, aren't they? So we can add these up. Divided by 1 minus the probability PP plus the probability of SS. So we plug the numbers into that. Then we get this lot here. And that comes to that. And we work that out to 0.23823 decimal places. So that is how that is. So that is the probability that the number of one of the tokens is a prime number, given that the numbers on the two tokens are neither both primes nor both square numbers. So excluding PP and SS. All right. So that's how we've done that, and we've used our leaf table here in order to do that. And of course, the important thing just to reiterate is that it makes it's made things a little bit easier, not actually having probabilities. The point is, of course, that all these would be divided through by that 14280, as would all these be divided by. So if we multiply the numerator and the denominator of this fraction by 14280, then this is what we get here. Okay. All right. So that's the trick that we've used there. In part 3, the number on the first token is a prime number, given that the numbers on the two tokens are neither both prime numbers nor both square numbers. Well, this denominator is the same as it was in part 2. So the first is P. So it's P something, given not PP or PS. So it could be PS, it could be PN. So those are the two events that we're considering. And out of this total probability space here on the denominator, in other words, we've excluded our PP and our SS. So again, multiplying through by 14,280, we get this. And that gives us that. And that comes to 0.2602 3 decimal places. So now that's actually quite a tricky problem. If you got that one in an exam, I think you'd be a bit unlucky. But to look at it a different way, if you can do this question, then there's you can do kind of most of these. And just to reiterate, yeah, a leaf table is good, but we might not need all the leaves. We can contract our sort of nomenclature here. Just talk about PP. We know that what it means: a prime first and then a prime second. That's all we need. Okay, so that is that particular problem. Now, just wanted to come back to this one. And the reason that what this is illustrating basically is the use of tables. So sometimes we might well be asked to put things into a two-way table. Some of those questions are quite straightforward. This one's is a bit more complicated because we're using the two-way table in order to be able to kind of reverse the conditionality. So this is the same we've seen in a previous video, in the conditional probability video. Patient goes to see a doctor. The doctor performs a test with 99% reliability. That is 99% of the people who are sick test positive and 99% of the healthy people test negative. The doctor knows that only, well, I've changed this from 1 to 2 because it's a little bit easier to see. We're getting a bit mixed up with our 1% otherwise. 2% of the people in the country are sick. Now, if the question is, if the patient tests positive, what are the chances the patient is sick? This is our original probability tree. I've not changed. This is still 1% here. But if we actually put this into a two-way table, no, we've got probability. This is 99% here. Probability of positive given that sick is 0.99, probability of negative given not sick is 0.99, and the probability of sick is 0.02. That's 2% prevalence of this disease. Okay, so what we've got is we've got our sick, not sick on the vertical, our positive and our negative on the horizontal. I've highlighted just so you can see what we're talking about. So each probability in here is the union. So this top left cell here is the probability of S. Oh, sorry, is the intersection probability of S intersection positive. Yeah. So and we start off by putting those into these bottom cells here, so that when we want the actual probability here, we are multiplying the probability of, well, it's this probability in here. So we're multiplying the probability of, this is the conditional, plus given S times the probability of S. And that's giving us the probability of S intersection positive there. Okay, and so on. This one here is obviously, that's the reliability of the test again, 0.99 for not sick, times 0.98. So that is that basically is the reliability. Yeah. And sorry, that's the prevalence of the disease. That's the reliability. Multiply those two together with 0.9702, and so on. And we can, a similar thing with these two cells here. So when we look at these, we've got the probabilities. So we actually now do actually have the probability of the test being positive. So, you know, some random person walking out of the doctor's surgery consultation room, they've had the results of the test because you get it there, and then if you sample these people, what's the probability that one person coming out of there who's had this test will have been positive? Then that's what that is that number there. Okay, so having got this table, then we can kind of use it whichever way we like, really. Now we want the probability of a person being sick given that they've tested positive. Okay, so the probability, so what we're doing is we're confining ourselves to this row here. So the total probability space that we are interested in is of size 0.0296. And the probability that we have in mind is this one here, 0.0198. So this conditional probability here is 0.0198 divided by 0.0296. Okay, and that gives us a probability of 0.66923 decimal places. This is a bit higher than when working through this problem in the conditional probability video, because obviously I've just upped the percentage to 2 there, just to make the numbers a bit clearer. So that is your probability of actually being sick if you have tested positive. So that I think is quite useful, and if you look at it in conjunction with the previous running of it, then I think that might clarify a few things for you. Okay, so that basically is all we need to say at this stage. So two kind of important ideas there. The idea that we don't necessarily need to draw the probability tree. Obviously, if the question says draw the probability tree, then you've got to do it. But if we're just working out probabilities, and we can visualize the probability tree from which it comes, then yeah, you'll just do the leaves, or just the leaves that we need. And the second thing is, if we need to do a two-way table, then there may be no conditional probability in a two-way table. You don't have to look for the conditionality. But if the question is expressed in those terms, then you'll need to apply it in order to get the probabilities in the middle. But what you are looking for in these cells here, these 4 cells in this case, is the intersection of the 2 events. Okay, so hopefully that's been useful, and we'll see you in the next video.